Hold on, let me. Okay, good. Well, as long as we don't miss homework, it's fine. It's fine. Hey, right here, see right here. So if I do have density function of f of y, how to maximize? How do I bring another variable z? Okay, then such that it's my marginal PDF. It's become like an integration of my joint PDF. It's okay, and then you don't actually observe z, and you're asking what? Okay, you bring in something you don't observe, and then that make your life easier. Okay, I do think they are genius. How they come up with idea, right? I bring up some random variable z, and then working on the joint PDF of y and z, much easier. Okay, let's see why they come up with this idea, right? But right now it turns out to be maybe your function about joint PDF of f, y, and z is easy to maximize, and then because y is observed data. Really, in practice, you only observe y. Z is hidden. That means z is just something you don't observe, but you can bring in, and you know the distribution of z, and you can working on things. Okay, good. So in general, would be you pick a starting point, theta z. Okay, then do each step, then do m step. In each step, you taking expectation on this kind of so-called complete Laplace function. Basically, it's assuming you know z, then you have y. Then I can write down complete Laplace function. Then I taking expectation with respect to z distribution is. Given that I do know about y and then all value of the theta j. Okay, that's what is expectation is. Okay, and then finding theta j plus 1 maximize Q function. Okay, again, if this step is still hard to maximize, then it's not worth of doing EM algorithm. Okay, doing EM algorithm is because original PDF is so hard to maximize. If a Q function right here still hard to maximize, then it's not worth of doing EM algorithm then. Okay, here's example. Let's read typical example when we talk about EM algorithm. Okay, in our class, we only know about what? Distribution follow what? Distribution follow normal, right? Distribution follow exponential. But in reality, sometimes your distribution is what? Mixture of two normals. For example, when you see data, if you see these kind of things right here. Okay, this is your f of x, this is x. Bimodal. Okay, if it's bimodal, there's no way you can find any distribution. Well, maybe find some really complicated PDF you can describe in bimodal situation. Yes, it could. But I can also what? See a mixture of two normalities. Okay, like a heights of men and women. Maybe men tend to be taller, women tend to be shorter in height. Okay, then if you don't know about information about their gender differences, then you will see height just bimodal. Okay, but then it could be easy to describe it by what? Combination, also called mixture of two normality it's. And then using a probability of pi, okay, to do connections. That means there's a probability of pi coming from this guy. Oh, probability of 1 minus pi coming from this guy right here. Okay, so that means I can write my PDF of y as a linear combination or mixture of two PDFs. And then two normal PDF have different mean, mu0, and then mu1, and then mu02 square sigma square 0 and sigma square 1 is. And then this is not necessary the mixture then. Sometimes people will say, hey, I don't want to get so complicated mixture. I want to make the sigma square the same. It's totally fine right here. Okay. Of course, likewise, you might think, hey, maybe they have the same mean actually, but have different variance. Yeah, either way. Okay. But the most general model would be I have a different mean, I have a different variance in a way of as a mixture of y-its. Okay, good. No question so far. Okay, sounds good. So then you know about PDF. Okay, you know about PDF. So that means straightforward local function, right? Okay. The point is how many parameters you have. Mu0, mu1, sigma square 0, sigma square 1, and as well as your pi, because you don't know how much, you don't know the proportion coming from here or coming from here. Okay, that's how I want to estimate as well. That means your theta actually have 5 parameters right here. Okay. Then when you're collecting y's, try to maximization to solving for theta to maximize, right? Could I do that? Argue max? Could I do that? Yes, you could definitely do that. But somehow you will think it's maybe more difficult because you need to working on that Hessian matrix, what? 5 times 5 Hessian matrix is. Okay? And then you do partial, double partial things, then you might end up having difficulties to deriving that Hessian matrix to solving for MLE. Okay, then there's some smart guys coming up. Okay, then how about introducing so-called latent variable then? Okay, I don't know who belongs to which group. I don't know which one belongs to which group. But what if I do know it? What if I know that this guy coming from 0, this guy coming from 1? Okay, like our assumption is, if coming from 0, first normality, coming from Z is 1, coming from second group, another normality right here. Okay, good. Then I can say that the probability of Zi belongs to this group is pi. Okay, so that means the complete equal function, like I suggested, join PDF between y and z. I can write f of z, then f of y and z. Okay, good. Again, it's z right here, binary, nothing but Bernoulli's. Right? Okay, this guy nothing but join PDF of Bernoulli. Okay, then right here is what? Right here, nothing but what? Given z, I know about y. That means if I zi is 1, follow this PDF. If zi is 0, this is 1 minus zi. Okay, if zi is 0, right? This guy, if zi is 0, this guy gone, then follow this guy. Follow this guy. Follow the first PDF. Okay, so combinatorial function, easy to find. And then how about each step then? Okay, so when we talk about each step, we always write Q function right here, each step right here. Taking expectation on the unknown variable. Okay, right now unknown variable is z. So that means given that observe, and a given O theta O theta. Okay, then taking out expectation on the log function. Okay, taking log right here, if taking log right here, log of f(y,z) right here. Okay, you should be able to find out this guy zi, then log pi I, right? Then I want to save my time, so I'm going to write detail. You know what I'm going to write right here. You're taking log on both consecutive product will become this. Will become this. Will become taking log become this, taking log become this. and then you take expectation until zi's. Okay, then expectation on zi is binary, nothing but what? The probability of zi equal to z. Okay, so from here to this equation, I just save space because you can definitely write out as you can write out pi I. No, I'm sorry about it's not pi I. You could write right here. You could write here it's probability of zi equals to 1 given that yi theta j, then times log pi, then plus 1 minus probability of zi. So actually whole thing should be, this guy should be probability of zi is 0 given yi, then theta j, then times log 1 minus pi x. You could definitely do that. And then eventually you'll figure out I can combine these two guys together to the expression right here. Okay? You can write this for sure. I'm just trying to summarize it in an easy way to do it. Okay? Good. So that means, however, is that you do need to pay attention to this Q function right here, still function of theta, given your theta OH right here. So that means looking at this whole function right here, where does your theta come from? Your theta is actually including right here. This whole thing is a function of theta. Okay? And keep in mind that this guy is not function of theta. Okay? This is a function of theta O, theta J is. Okay? Good. So that means when you do your maximization, okay, the key is that it's how do I deriving this part, although it's not function of theta, but can I first
I can't hear you. I'm sorry.
You freeze for a moment, but you're good now.
Hello? Hello?
Hi.
Oh, sorry. How much you guys miss?
Um,
Until what? Until which page?
the end of page 8.
Page 8.
Yeah, not a
Oh, I
function
really
of.
have no idea about I lost the connections.
Yeah, you were
Okay.
just finishing that the first part is not a function of theta, but of theta j.
Oh, okay. Not much, right? Oops.
But we
Page
can't
8.
see your screen.
Yeah, I do know you don't see my screen, but I'm trying to give you my screen right now. You guys see that? You guys see that?
Yes.
Okay, good. So page 8. Okay, so yeah, I do need to pay attention occasionally about missing connections, right? There's no sign showing tell me that my connections are missed. Okay. Yeah, where we are, so you're saying it, I'm talking about, okay, it's not functional state. Yeah, you do need to, because when you do maximizations, you do need to know which part you maximize. Okay, the second part is functional theta. Okay, the first part is not functional theta. Okay, then the point is with deriving the probability of zi equal to z right here, and given yi as given observe, again given observe, then okay, hold on, let me chat. Hold on. Okay, sounds good. Observe this guy is O, theta O right here. Okay, but nothing by Bayes rule, and you can working on this guy become denominator, then above become join PDF, Okay, so since that I can definitely write out again as UI ding dong as a given, then the distribution of z equal to z become join PDF, straightforward. And this guy right here is nothing but just summarizing of z from z to 1, f of zi, then yi, then given theta j then. Okay, still straightforward as well. This guy in the denominator, in the numerator, sorry about this guy in the numerator. So as long as you know the numerator, you can just put that summation z from 0 to 1 then. Okay, then look at the numerator. Easy to derive because I do know this guy is what? This guy given zi is z, then I do know y it's depending on what zi is, one of the normalities. Okay, then the probability of zi right here is nothing but what? Bernoulli distribution. Okay, good. But because given theta j as O, so this guy pi right here is O as well, pi j, then mu, and then sigma square also indexing by j because I given theta j is O. Okay, by doing so, the maximization over that Q function, you can actually solve in that analytically in this particular problem, but sometimes you won't. But this perfect example is you do have that. Then that means that it's looking back to Q function right here. Okay, this part be deriving from this page, right? And then this part is actually a function of theta. Then you maximize over the function of theta right here. You could actually derive it by hand. Okay, I don't have time to show it because I don't want to file homework. Then it's not hard to find that actually, but because that really looks like when you're deriving of the when you're deriving MLEs for binomial, for Bernoulli, and for normality. Imagine this is so. Imagine, let me see if I can say something more straightforward. You will see that it's so. Like I said, this guy only function of theta, right? Then when you derive it, this guy only function of pi i's, right? This guy is only function of mu1, mu0, sigma square, sigma square 1, then sigma square 2x. So then imagine when you do your first derivation, right? You partial pi I, whole thing is gone. This guy nothing but what? Like you solve for Bernoulli distribution, like you solve for your MLE for your Bernoulli distribution. Then when you partial mu1, mu0, or sigma 1 square, sigma 2, 0, this guy is gone as well. Then this part, nothing but what? Maximization over MLEs under normality. So no wonder you will see that right here. It's everything look like what? This guy look like weighting means of y's to get your mu. This guy is weighting standard deviations to get your sigma square. And then this guy is nothing but what? Counting how many zi to be 1, right? Each one having a probability of zi equals 1. This guy nothing but what? Average it to get your pi I. Everything is closed form. You do iterations pretty quickly. You don't even do solving for anything numerically. Then getting started from theta 0, and then you do iteration, get mu1, get theta sigma square 1, and get pi 1, and then you do mu2, sigma square 2, then pi 2 until convergence, until convergence. Okay, then how to do with convergence is really something that I'm saying is the bunch of criteria. For example, it's you can say pi I plus 1 minus pi j right here was more than some curve 0.001, for example. You could call that as convergence already. Or sometimes maybe restrict saying it's I want to everyone simultaneously convergence. This is J. I want everyone simultaneously convergence. I only write 2. Hope you know what I'm saying. Something like that. Okay, so I can using the lousy one. If lose one, I can use a more straight one right here. Okay, for everyone to simultaneously convergence, then you can stop. Then call that is your MLE. Okay, so I don't think I have time to talk about how MLE work because I do want to call homework. But this slide right here really saying it's okay. Eventually, we are trying to say this, right? So EM algorithm just nothing but helping you to find MLE. So that means if I want to say theta 1, theta 1, theta 2, then until theta head, right? This is my goal MLE right here. I do want my theta from theta 1 to theta 0, but improving my Dipole function is. Right? Otherwise, it's that doesn't make sense, right? Then the point is, but I'm not maximizing log Dipole function here. Right? I'm not maximizing this. I'm maximizing Q function. Okay? So that means we somehow need to prove that it's if my maximizing Q function actually implying this, that means not only about Qj plus 1 given Qj, got to be bigger than Qj given Qj is. Not only that, but also by doing so implies to L theta j plus 1, and then I'm trying to see if I still online, then j given y. I need to show so. Otherwise, there's no meaning to maximizing the Q function in my EM algorithm. It's okay. Let me see. Good. Okay. So let me stop right here. The whole thing is trying to show so, and then really easy to prove is what is saying it's okay. I divided the J function right here, then based on Q function minus this guy right here. This guy is not a function of theta, not a function of theta. So that means maximize Q function is the same thing as maximize J function. Making sense? Okay. So that means whenever I maximize J function, I show this. This is my goal. Okay, this is my goal right here, bigger than 0. And then because of that function, the difference, this guy is easy to show. I don't have time to tell you the detail. You could try it a little bit to show you by yourself. I just want to talk about results. Okay, so this guy, if you can show this thing right here, eventually it's what? This guy becomes this guy plus this guy. This guy is Kuiper-Leber divergence. Okay, then we mentioned that before, but we don't have detail. Then again, is this guy also bigger than 0 by that property of Kuiper-Leber divergence. And then if I can show this guy bigger than 0, then I have that results right here bigger than 0. Okay, it turns out to be, it's not really hard to show that because this guy, so I'm sorry. So this is what I'm trying to show, right? This guy, okay. Then this guy right here is you're trying to maximize, right? You maximize Q function, the same thing you maximize J function. That means your theta J plus 1 is bigger than theta. Plug in right here as a theta J, right? You maximize your Q function given that theta. You maximize your Q function given that theta J. So it means Qj plus 1 given, this is nature. This is nature. Okay, good. And then, but again, it's if I plug in theta J to the J function right here, then the whole thing becomes 0. We're going to put a form of it right here, right? Right here. I can write theta. I can write J function as this way. And then if you're replacing theta J right here, everything becomes theta J. As you can see, is nothing but what? Log 1, 0, log 1, 0 as well. So that means as long as you're replacing theta into theta J, this guy is naturally 0. That means you can prove that this guy bigger or equal to 0, right? Okay, good. So that's really a little introduction about how EM algorithms will work. Okay, but this is only like a standard lectures about EM algorithm. In your future life, you might again, if you are dealing with, for example, missing data. Okay, for example, you're dealing with frailty model. Okay, you have a bunch of like in some sense of missing mechanic in your data set, then you able to develop your own EM algorithms. Okay, follow the same principle. Sometimes EM algorithm is hard to do actually, but sometimes EM algorithm is straightforward, like the initial problems. I always using EM algorithm to solving my questions. If I have a chance, I want to introducing my own research to you and for you to see how I using EM algorithm to working on real practice problem solving. Okay, but we don't have that time right now, so let's go to the homework. So hopefully you guys don't feel like worry about how you're going to finish that as a homework, right? Okay. But I do need some time to do something about showing my whiteboard, like we do discussion. So give me some time to switch that. No, it's not. What should I do right here? I think I just, okay. So then I will popping out whiteboard like I did. So you guys see my whiteboard, right? You guys still there?
Yeah.
Oh, okay, sounds good. Sounds good. Thank you. Appreciate it. Let me know. Okay. Okay. So in a homework, let me pull out let me pull out homework questions. Okay. So okay. Okay, good. So in a homework number 6, you do have what? You do have x1 to xn. So you see my writing, right? You see my, okay, sounds good. You do have your x1 to xn. Follow PDF, you do alpha and beta, right? And then equals to 1 over beta exponential, then sort of shifted exponential. You saw that before. Okay, divided by beta x. Okay, of course, your range of x depending on alpha, then small infinity, then alpha is in real line. Okay, we can save that, solve this standard drill. Okay, so then you are finding U and VUE. Okay, again, there are two methods, right? Method number one. Okay, I don't want to repeat. Basically, it's you find unbiased estimators. Then given that unbiased estimators are W, I think it's W. You finding the complete sufficient, right? Complete sufficient statistics, unbiased. You find U and VUE by dimension of A. The second one, much easier. Okay, you should working on your TX directly. Okay, hopefully A plus B tau theta. Then you do know how to solving for unbiasedness. Then for tau theta. I do want to give you much more of this. There are a lot of real questions right now. I can share that with you using method number one. I think this method, oh, maybe D is actually using that method. Method number one, it's okay. Let me see. Okay, good. And then I think A. Let me pause solution key. Okay. So if you could using method number two, then it's really easy for you. Okay, you don't have to read the writing really lousy, really how do I say that? It's really real approach about deriving the expected value of unbiased estimator given that. Okay, good. By any means is you need to find that complete sufficient statistics. Okay, good. So in A is what? And in A is say if I do know about beta, then what's U and VUE? U and VUE for alpha then? For alpha. Okay, good. So right now I did not really emphasize this before. That's the reason why I want to talk about it right now, rather than 3 o'clock. Okay, so alpha, say, if you don't have any idea about alpha, which estimator you should use, right? Okay, we are talking about complete sufficient statistics for alpha. How do I find it, right? You might want to say, hey, number one is, I'm using what? Factorizational theory to find sufficient statistics for alpha. Okay, then how about completeness then? Right? Of course, one thing you definitely don't want to do is what? Using exponential family. You should know that right now is why I cannot using exponential family right here for alpha. The reason is if I beta fix, the whole PDF is not exponential family because your range of x depending on alpha. So basically, you forget about using exponential family. Okay, but I still have one factorial theory could give me sufficiency of alpha. Then this guy right here, I never really talk about it. Okay, although in 661 I say you guys should know it how to derive. Let's do that right here. And this is a standard approach. And if you are trying to find answers using Katzenberger's solution keys, you'll find out how to do it. So again, it's sufficiency. I think I don't want to talk about too much right now. So because I think you guys know, I don't want to keep talking about this kind of things. It's alpha is x1, right? no, alpha hat is x1. Okay, that means x1 is your sufficient statistics. Okay, right? Using the factorial theory, you will know that x1 is, sorry, alpha sufficient statistics. Then how do I show that x1 is also complete statistics of alpha then? Using definition. Say a g function of x1 right here. But the definition is only unbiased function of zero function. G is a zero function, right? It's what definition of completeness is. Okay, good. Okay, I'm still there. Okay, good. Yep, sounds good. Okay, so then that's our goal is show G function is a zero function. Okay, because this is expectation, then just go by definition then. But definition is what? I can using definition of expectation, right? I have Gx right here. This guy right here is a PDF of x1. Then dx. Then this guy right here, alpha from 0 to infinity is, right? Okay, that's by definition of expectation, right? X1 is a function, Gx1, this guy is a function of x1, right? Function of x1, by definition, expectation, nothing but what? Taking G function times the PDF of x1s, then do integration. Then I could get the derivative, I could get the expectation of Gx1 is. Then it comes down to what is the PDF of x1 then? You do know about the PDF of individual one, right? So I assuming you should know how to deriving the PDF of x1s, either using formula, either using CDF methods, whatever that is, use that. But I don't want to waste time by doing that. I'm going to give you directly what that is. This guy, nothing but, not surprisingly, is actually it's one shifted exponential, because x1 to xn exponential, minimum order statistic would be also exponential as well. Okay, then this guy right here would be having that n, right? If you remember x1 to xn, if that exponential beta, then x1 is follow exponential beta divided by n, meter number 1, if you remember that. Okay, similar things right here. Okay, you should know that. So similar things right here. You have your x still bigger than alpha, smaller than infinity. Okay, the same range about x1s. Then coming back to previous slides right here, right? I'm going to plug in PDF right here. So that means the EGX1 is going to become alpha to infinity. Then FGX1 is then GX, then N beta minus 1, E minus N, X minus alpha divided by beta, right? PDF of X1, then DX. Okay, good. So one tricky part is right here. If I do derivation to differentiation on the left hand side, see what will happen. Remember Leibniz rule? If you do d alpha right here, you do have alpha right here, right? So you cannot just do direct differentiation. You need to using so-called Leibniz rule, if I still spell correctly. Leibniz rule. Then what is Leibniz rule then? Okay, I'm a little bit tired, so right. my voice kind of spoiled a bit. I need to do something else. Okay, I'm back. Then is what? Actually, you plug in this guy up, right? You plug in this guy, then do differentiation. Of course, this guy, you don't have to do anything because it's zero. It's no function of alpha, right? And then you plug in this guy right here. You plug in G alpha, then n beta inverse exponential minus n, then alpha minus alpha divided by beta. Then you d alpha, then alpha, then. It's called Leibniz rule. Okay, good. So that means by doing that, you'll find out this guy is 1, so you don't have to take care of it. This guy is 1, and then this guy is 1 as well. Okay, then you set it if this guy is 0, implies that G function is 0 function. What happens? This guy is 0 as well because of dd alpha, right hand side still 0, and the whole thing what right here is positive, right? N positive, beta positive, inverse positive 0. That implies your G alpha is 0 function then. So that means your G is 0 function. So that means your X1 is a complete statistics. Any question on this? I want to make sure. Hello? You guys hear me? Okay, sounds good. Thank you. Okay, so that means using that, I can show that X1 is a complete statistics. Then along with the factorizational theory, I got sufficient statistics as well. So that means X1 is complete sufficient statistics. And then, because I do know X1 is complete sufficient statistics, again, I'm going to do this, trying to cross my fingers to say that's A plus B theta, right? I think so, theta. Oh, actually it's alpha. Okay, good. So right here is what? Right here, really just expectation of X1, and you do know about the PDF of X1s. So straightforward, right? Doing your derivation of expectation of X1 using PDF of the X1s. I don't want to waste my time. I could told you the answer is what? The answer is alpha plus beta divided by n. Great. I'm looking for alpha. This guy is my B, right? That means it's what? I can do that. X1 minus B beta divided by n equals to alpha. Okay, I think so, right? Let me make sure that I don't mix anything. Yep, I think so. So that means this guy right here, okay? This guy right here, again, function of complete sufficient statistics. Bias as well. So I can claim that it's X1 minus beta divided by n is U and V U E. U and V U E by Lemon-Chaffee. Good?
Excuse me, Dr. Lin, I have a question.
Yes. Yeah. Go ahead.
I think the partial derivative on alpha is not correct.
Why?
You should derive on the alpha on the integral sign first, and then derive on the exponential function, because there's another alpha.
Oh, yeah, you are correct.
Yeah.
Oh, okay. Sorry about that. So you plug in alpha, and then you have another function.
Yeah, and then you have another integral.
Right.
Yeah, but the result is correct. I also use this one to prove the complexity.
Right. That's a good approach. That's the right approach.
Mm-hmm.
So you do need to follow. Yeah, I forget about this inside integral is a function of alpha as well.
Yeah.
Okay, that means you need to do like a chain rule, right?
Yeah, it's like a chain rule. It's like a derivative on the production.
Yes.
Yeah.
Okay.
Mm-hmm.
Yeah, okay. Anyhow, right here, I will leave it to you. Okay, you could check out what the Leibniz rule is. Okay, and then eventually you sort of go through this kind of things, claiming that G function is alpha. Yeah. Okay. Yeah. Sorry, really tired right now. Okay. Good. So then let's go on to the second one because I don't want to occupy too much of your time. Okay. Then the second one is much more. So, okay, if you cannot figure out, you can call me on Wednesday. You can let me know I have done on Wednesday. So you let me know I can go with the full derivation of Leibniz rule to you. Okay. So then in a B, much straightforward. Okay. Because we don't have to working on all the statistics claim that your X, don't working on all the statistics claim that complete sufficient statistics. So in B, it's U and VUE of beta when alpha is known, right? Okay. So that means again, I'm trying to find what complete sufficient statistics for beta then. Okay. Then I'll leave that to you because whenever alpha is known, then diffusion become exponential family. Using the property, you'll find out is summation xi is complete sufficient statistics for beta. Okay. Again, you have complete sufficient statistics, then as a summation xi, then take expectation on summation xi then. Summation xi then. Okay. I fully trust you'll be able to do it, right? Well, this guy nothing but n times exponential ex1, right? And then nothing but what? This guy n is what? I think ex1 should be alpha plus beta. Okay, I fully believe you guys can do it. Okay, with alpha plus beta. Then again, it's, yeah, good news. Again, you saw that a plus b, then tau theta. This is my target. So that means I can do this. Summation xi minus n alpha, then divided by n equals to beta. Again, inside that would be function of complete sufficient statistics and biasness. So again, this guy is a UMVUE by Lehmann-Schaffer. Okay, good. This is nothing but x bar minus alpha, right? I think so. X bar minus alpha. Okay. So in C, to find UMVUE of beta and alpha, here you may assuming that it's summation xi, x1 are complete sufficient directly. Okay. So it means you just find some combination trying to find. Let me see. Okay, let me take out some of that because I think you guys know that already. Right? Okay. So again, we do have x1 without any proof. I do know that this guy is a complete sufficient statistics. Then I'm trying to working hard to find that statistics as function of complete sufficient statistics. Then it's unbiased estimator for beta or for alpha. I think you could try this summation xi then minus n x1 is. Okay, because I do know that exponential expectation summation xi minus n expectation x1 is what? This guy here, n alpha plus n beta minus n. This guy is what? This guy is, where is that? Here, right? Equals to a alpha plus b divided by n. Alpha plus beta divided by n, such that n alpha taking out. This got n beta minus beta, n times n, so become n minus 1, then beta then. So that means using this guy right here, I can have in that a plus b, a plus b tau theta. So I can just put n minus 1 in the left-hand side, so I can isolate beta right here. Okay, a little bit tricky though, because you might know this kind. I mean, you just try and error. You know, you do know about combination of the. You do know less. You also know less. So in a tricky way of you trying to manipulate. How do I get that function? How do I get this function right here? Then eventually isolate beta in the right hand side. Okay. Then you do things similarly for alpha, right? I think alpha is what? So try this. So using this guy also, x1 minus, oh wow, n times n minus 1, then summation xi minus n x1 x. Okay, then try this and then taking expectation. Okay, and then to see if eventually you could isolate. Let me see. Do I have any clue about this? Well, you do know about betas. You do know about betas, U and UE, right? You do know about betas, U and UE. Then I think you basically just plug in right here. You plug in beta right here. You plug in beta right here. Then you get the alphas. You know what I'm saying? Okay, I'll say again. So hopefully you understand. So you do know about beta. You do know about U and UE for beta is this. Summation xi minus n x1 divided by n minus 1. You do know this guy is beta hat. You do know beta's U and UE is this. Say beta hat right here. How about I say so? Beta hat right here. And then you also know about expectation of EX1. You also know this. Alpha plus beta divided by n. Then to isolate alpha, I will just plug in head right here. Then become expectation x1 minus beta head divided by n will become alpha h. Well, inside guys still function of sufficient statistics. So using that way, you can isolate alpha in the right hand side, such that by Lehmann-Schaffer, I can claim that alpha's U and UE is x1 minus beta head divided by n. Okay. Oh, wow, I think D is most challenging. I think basically you might not having that. Okay, great. Okay, if you still have time, hang in there. Okay, so we are going to D. So assume beta is known. Okay, then find a U and UE for probability of x1 bigger than t. Okay. So it looks like it doesn't have a straightforward way to using method number 2, like taking any, you don't even know what this look like, right? This guy definitely tau theta, right? Function of theta, it's, okay, function of, so right now it's because this guy, it's, you're looking for a function of alpha. Beta is known, right? Yeah, alpha is unknown. And this guy definitely is function of alpha. but you don't even know what the function look like. You don't even know tau function. Then I don't think you have a way to using, take expectation on some complete sufficient statistics. Then you might want to a second way then. Let me see. The method number 1. Okay, let me see if I do have a bias estimator. Oh no, I actually using method number 2. Okay, let me stretch a little bit. Good. So, first of all, what does the probability look like, right? So, based on PDF, what? Hold on. You guys can hear me? Hello? Okay, yeah. My pen doesn't work right now, so I'm trying to do something else. Sorry about that. Okay, so what? Oh my God. Okay. My previous board doesn't disappear. So well, hopefully it doesn't bother us. So okay. So what's the probability of x1 bigger than t look like, right? By the PDF of x1 right here, right? You have PDF. I don't have board right now, so I don't have previous board right now. So you guys can deal with that. You do know about the PDF of x. You should be able to derive in its probability. Let me give you that. Okay, so expectation minus t minus alpha. What? Divided by beta. Then t bigger than alpha. Okay, let me see. Is that reading well? Okay, good. And then 1 if t smaller than alpha. Okay, good. Okay, and then, so let me see. I do know probability is that way. Then, so if I actually using the method number 2, method number 1 is, if I trying to find, okay, my brain sounds stuck. So, so if I can find a g function, expectation g function of x1, it's okay. Okay, hold on. This is my tau alpha, function of alpha. Okay, if I can find any complete sufficient statistics, I do know about x1 is the complete sufficient statistics. I'm finding a g function right here. If that's this is unbiasedness things, right? Okay, yeah. So by demonstration, I don't know. The goal is trying to find g function. If I can find g function, oh, well, hold on. My pen doesn't work well right now. Oh, we are talking too much. Okay. So if I can find G function, then by Lehmann-Schaffer, I do know what the by Lehmann-Schaffer, I do know the G function. I also know that X1 is complete sufficient statistics. So that then I can claim that GX1 is the UMUE, right? So point is, what's the G function then? What's the G function? Then that's our goal. Our goal is trying to find G function. I think it's the same thing as trying to show that X1 is trying to show that X1 is complete statistics. So if you really do that right here, then you basically is what? You have your alpha 2. This is range of X1s. Then, yeah, PDF. Okay, I don't have that in the passports. I do have that right now. PDF, it's not beta. This is infinity. And then I do have a G function right here. G function is our goal. So I have a G function right here. So good for me to do it. Then the PDF of X1 is n divided by beta, then exponential minus n x minus alpha divided by beta, then dx. Okay, so I think we are doing the same thing as we showed our complete statistics, right? That's why we can isolate the G function is. That means we are going to do d alpha like we did then. Right, and then d alpha, because this guy right here, if you do differentiation, this you d alpha right here, not equals to 0 like we did in common statistics, your left hand side 2 equals to this. So that means you're actually dx1 bigger than t. Okay, good. And then, so in the right hand side, maybe easier, okay, only if you forget about this, because every t bigger now is bigger than alpha. Okay, so you d alpha in the right hand side equals to what? Exponential minus t minus alpha beta right here. Okay, chain rule, right? Chain rule is what? Shoot, I don't have brain right now. Chain. What?
1 over beta.
1 over beta?
Yeah.
Wait, chain rule. Oh yeah. Yes. Okay. Okay. My brain is stuck right now. So 1 over beta. Thank you so much. Yeah, 1 over beta. Okay. So the point is, what's your right hand side, left hand side, and what is this guy right here? Okay. Again, applying Leibniz rule to get results. Okay. So I don't want to embarrass myself. Let me just give you the result directly. Let me see. But well, it's not that hard to derive, right? So I think you can just bring in alpha out then. I think so. You can have d alpha. Yeah, just bring alpha out. Then you don't have to deal with the double integration, double differentiation. That means I can bring alpha out. I can bring alpha out, so that means I will leave x inside. So I have n alpha out divided by beta, right? And then this guy is not necessarily inside that alpha as well, but I do need to maintain the gx inside, then exponential minus x, right? dxx. Yep, that might be easier for us to do differentiation, but we do need to have in that this guy functions alpha, this guy functions alpha as well. You do product differentiation on product. Okay, so that means you d this guy first times this guy, then this guy first times this guy. Okay, so I think let me just write the result, right? Could I do that then? Let me see. Do I have a results right here? Alpha, alpha on both sides of alpha. Okay, so let me write a result first because it's late right now. So you guys working on it, okay? So as I said, the alpha exponential and alpha divided by beta. Then either way, right? So you do d this guy, then integral alpha infinity that guy. Okay, and then you d, then plus, right? Plus d another one. Okay, say if you cannot handle it, let me know. I can do it on Wednesday. Okay. Let me give you a final one. Eventually, you will get this equation, and e divided by beta, then g alpha, then exponential minus n alpha divided by beta, then equals to n minus 1 times exponential minus n minus 1 alpha divided by beta. Okay, to see if you can get equation. But again, it's don't forget about you have a right hand side like this. Okay, you're working on left hand side to see if you can get this equation. Okay, then if you can get this equation, then you can basically isolate g alpha out. The goal is trying to find g function. So I want a g function on the left hand side. Then you're just working on a bunch of simplification, trying to move it on to the right hand side. Then how much I can do? Let me see. I can exponential right here. This guy is exponential minus n alpha divided by beta exponential alpha divided by beta, right? Minus, let me see, double check. Yeah, I think so. So that means this guy cancel out. And then this guy divided by that, I think eventually it's alpha divided by t divided by beta, I think. Yes. Okay. So that means your g function is n minus 1 divided by n exponential, then x minus t divided by beta. Then that means the expectation of gx1 is a UMVE, right? UMVE. Then that means your g function of x1 is n minus 1 n exponential, then x1 minus t. I don't like t at all. I don't like t at all. So g function. Oh yeah. Oh, I'm really tired. So t is the constant. So I thought t is a statistic. T is a constant right here. Okay. So that means minus t, then divided by beta is a UMVE. Okay. Okay. So I think so. Let me double check it. Then of course, if you want to write more specifically, if your x1 is more than t. Okay, good. That's in D. I don't know, it's messy. So if you cannot get this equation, let me know. Okay, we can work on that on Wednesday's office hour. Any questions? Okay, if not, I will see you on Thursday or Wednesday maybe. Okay, you guys have a good one. Bye-bye.
Thank you.
Thanks.